What if the deepest, most mind-bending mysteries of the universe, like, the way black holes behave, could actually be understood using something totally modern, something like machine learning? Get ready for a deep dive that might just connect the cosmic dots in a way you really never saw coming. Welcome to the deep dive. We take complex ideas, peel back the layers, and, well, serve up the fascinating insights. Today, we're plunging into a truly groundbreaking new paper. It's proposing this really surprising, profound connection between that cosmic puzzle, the black hole information paradox,
Right.
and this weird phenomenon from AI called double descent in quantum machine learning.
That's exactly it. Our source for this deep dive is this recent research paper laying out this, well, novel correspondence. And our mission for you, the listener, is to really get how these two fields, which seem incredibly complex and totally separate,
Yeah, completely different worlds.
might actually be speaking the same language,
So,
offering totally new ways to look at both.
Yeah.
It's potentially a huge cross-disciplinary thing.
okay, let's try and unpack this because, yeah, these are two intellectual heavyweights we're talking about. On one side, the black hole information paradox, a cosmic mystery that's, stumped physicists for ages.
Decades, yeah.
And then the other side, double descent, a pretty recent kind of algorithmic surprise from AI. We're going to dig into how they share these really uncanny parallels. Almost like the universe is, echoing its own rules.
So let's start with the black hole information paradox. Um, at its heart, this is a deep conflict between two pillars of modern physics, quantum mechanics and general relativity. Quantum mechanics basically dictates that information fundamentally just can't be lost from the universe.
Right. How should we sort of picture that? Is there a simple way to think about it?
Well, think of it like shuffling a deck of cards. If you start with an ordered deck and you shuffle it perfectly, the information about the original order isn't gone.
It's just mixed up.
Exactly, it's just scrambled. If you knew every single move of the shuffle, you could, in theory, put it back exactly as it was. Quantum mechanics says the universe works like that. Information always sticks around, even if it's really hard to find.
Okay, makes sense. But then black holes, they mess everything up.
Precisely. Stephen Hawking's work using general relativity suggested that when stuff falls into a black hole, the information about it just seems to vanish forever when the black hole eventually evaporates.
Through Hawking radiation, right?
Through Hawking radiation, yeah. And this directly clashes with that core quantum principle called unitarity.
Unitarity, that's the idea that quantum stuff is reversible, like you can rewind the tape.
Essentially, yes.
Yeah.
If you could run the process backward, you should get back exactly where you started. But Hawking's calculations suggested black holes were like cosmic information shredders.
Which sounds like a massive problem for physics.
Oh, it created a huge theoretical headache.
Yeah.
A full-blown crisis, really. If information is truly lost, it fundamentally breaks quantum mechanics as we know it.
Yeah.
It's like saying you can just make those playing cards disappear, poof, gone forever.
Not just shuffled, but actually gone.
Right. And that tension has fueled, well, decades of intense debate. But there's a critical point in this whole evaporation process, a sort of transition point, that most physicists accept. It's called the page time.
The page time, okay.
And this is seen as the moment when information starts to leak out, to emerge from the Hawking radiation. It's a really pivotal concept, and it sets up the parallels we're about to get into.
Okay, so page time is key. Now let's jump over to the other side, machine learning. Traditionally, the thinking was pretty clear. Make your model too complex, give it too many knobs to turn, too many parameters, and it just memorizes the data it trained on, it overfits, and then it's terrible at handling new stuff.
Exactly. You'd see the test error, how well it does on unseen data, go down at first as you add complexity, but then it would start to climb back up, especially around this point called the interpolation threshold.
Which is where the model has just enough complexity to fit the training data perfectly.
Roughly, yeah. Where the number of parameters, let's call it P, is about the same as the number of training examples, N. And the intuition was, okay, now it's just fitting the noise, not the real patterns.
Makes sense. But then something weird happened, especially with these huge modern neural networks. What was the surprise?
This is the double descent phenomenon. It turns out, after that error goes up near the interpolation threshold, it can actually start to go down again.
Wait, what? It gets worse and then it gets better again, even though it's way more complex.
Yes, in what we call the overparameterized regime, where P is much, much larger than N.
That feels completely backward. How does that even work?
It really does feel backward. But this surprising recovery in generalization, meaning it gets good at predicting new data again. It seems to be linked to the statistical properties of how these enormous models represent information. There are these sort of hidden mathematical structures that emerge when you have just tons and tons of parameters. Frameworks like the Marchenko-Pastor law help describe these patterns and explain why the models suddenly seem to get smart again.
Wow, okay. And you mentioned this isn't just for standard AI. It happens in quantum machine learning, too.
It does, yeah. It's been observed in QML models as well, which suggests that maybe even quantum computers could benefit from being massively overparameterized, pushing past what we thought were sensible limits.
Okay, so we've got black holes possibly destroying information, but maybe releasing it after the page time.
Right.
And machine learning models getting worse than better as they get super complex. Two really strange phenomena. And this is where the paper draws this incredible connection.
Indeed. It proposes this novel and, frankly, pretty uncanny correspondence between the black hole information paradox and this double descent behavior in QML systems.
So they're saying that recovering information from Hawking radiation is like a quantum computer doing regression?
Essentially, yes.
Yeah.
They interpret the whole process as being analogous to linear regression, but done over quantum states.
Yeah.
It's like the black hole itself is a quantum system trying to learn about what fell in by analyzing the radiation coming out.
That's wild. How does the mapping work?
Well, they map to different stages or regimes. So the early stages of black hole evaporation, when only a little radiation has escaped and the information seems lost. That corresponds to the underparameterized regime in QML, where the number of radiation outputs is less than the number of internal black hole states.
Okay, not enough parameters or not enough radiation yet.
Exactly. And then that critical point for black holes, the page time,
Yeah.
that maps directly onto the interpolation threshold in QML, the point where things get tricky.
The point where P equals N, or the radiation degrees of freedom equal the internal states.
Got it. And then crucially, beyond the page time, when lots of radiation has come out, the information becomes recoverable from the black hole system. And this mirrors the overparameterized regime in QML, where the model starts performing well again, even though it has way more parameters than data points.
It's like the black hole has finally emitted enough data in its radiation for the learning to work again.
That's the analogy. And the key thing tying it all together is this ratio they call alpha.
Alpha, okay.
In machine learning, alpha is just p divided by n parameters over data samples.
Right.
For black holes, they define alpha as omega, the dimension of the radiation space, divided by e to the s, the exponential of the Bekenstein-Hawking entropy, which counts the black hole's internal microstates.
So omega over e to the s, it's basically radiation complexity versus black hole complexity.
Precisely. And this alpha ratio, this O's, acts as the bridge. It tells you which regime you're in, whether you're talking about QML or a black hole evaporator.
Wow. Okay, so what's the evidence? How deep does this connection actually go?
Well, one really deep piece of evidence is in the math itself. Specifically, the spectral structure, like the pattern of eigenvalues, of something called the reduced density matrix of the radiation during evaporation.
Okay, that sounds complicated.
It is, but the key point is that this structure shows a specific kind of symmetry, an inversion symmetry, related to that alpha ratio. And remarkably, this is the exact same kind of symmetry found in the Marchenko-Pastor distribution, which, remember, helps explain double descent in large random matrix models used in machine learning.
So the fundamental mathematical pattern governing how information shows up in Hawking radiation matches the pattern in these complex learning models.
Exactly. It's not just a surface similarity. It suggests the underlying mathematical machinery might be shared. That's pretty profound.
Yeah, that's genuinely mind-bending. What else supports this idea?
It gets even more compelling when you look at variance, or sort of the error. They model the black hole information recovery as this quantum linear regression problem, and they calculate a quantity V, which is like the test error variance.
Okay, like how uncertain the prediction is.
Right. And what they find is that this variance, V, diverges. It shoots up infinitely, mathematically speaking, right at the interpolation threshold.
Which is the page time, alpha equals 1.
Exactly. The paper even has a figure, figure 1, showing this sharp spike in variance precisely at E equals 1. And then the variance decreases on either side. It perfectly shows the double descent pattern, but for black hole information recovery.
So that peak, that divergence, is like the moment of maximum confusion or instability for the black hole's information release. Just like the model hitting that overfitting peak before getting better.
That's a great way to put it. A moment of intense uncertainty as the system transitions. The paper calls this divergence a quantum susceptibility.
Like in physics, how materials respond near a phase transition.
Precisely. It acts as a strong indicator of a quantum phase transition happening in the information retrieval process. It signals this fundamental shift in how the system behaves, kind of like water turning to ice at 0 degrees.
Okay, so what is changing fundamentally at that page time, at alpha equals 1? What's different about the information before and after?
Good question. So before the page time, when alpha is less than 1, the radiation coming out is, well, quantumly speaking, its description, the reduced density matrix, or it's full rank,
Full rank meaning what?
meaning essentially all possible states within that radiation subspace are occupied. The information about the stuff that fell in is technically encoded in the correlations within the radiation, but it's completely scrambled and inaccessible to any observer outside.
Okay, so it's there but hidden, like the shuffled deck.
Very much so. In the QML analogy, this is the underparameterized regime, the model just doesn't have enough capacity or the right structure to pull out the signal from the noise.
But then, after the page time, alpha is greater than 1. What happens then?
Then it flips. The radiation space becomes, in a sense, overcomplete. You suddenly have more than enough basis states, more than enough pieces, to reconstruct the original information. The reduced density matrix, R, becomes rank deficient. And this is where these things called zero modes appear.
Zero modes.
Think of them as special channels or directions in the radiation state space where the effective noise cancels out, allowing the original signal, the information about what fell in, to be clearly recovered.
Ah, so the structure changes to allow the information out cleanly.
Exactly. In QML terms, this is the overparameterized regime where generalization surprisingly recovers because the model finds these simple solutions hidden within its vast complexity.
So the black hole has basically emitted so much training data, the Hawking radiation, that you finally have enough structure in that data to figure out the original input.
That's the core idea. The information isn't just present, it becomes accessible due to this structural shift. The paper talks about an inversion of informational roles, meaning what was hidden and inaccessible before the page time becomes accessible after, and perhaps vice versa for some other complementary information. It's a fundamental reorganization of how and where the information is stored and how you can get at it.
That's fascinating. And you mentioned a dictionary.
Yeah, they actually include a table, Table I, that explicitly lays out the black hole QML correspondence dictionary.
Yeah.
It's really helpful. It maps, the dimension ratio alpha, Hilbert space ratio, radiation versus black hole on one side, parameters versus data samples, PN on the other.
Right.
The critical point, alpha equals 1. Page time for the black hole, interpolation threshold for QML,
Makes sense.
then alpha less than 1. R is full rank, information hidden, maps to the underparameterized regime, and alpha greater than 1. R becomes rank deficient, those zero modes appear, information accessible, maps to the overparameterized regime where generalization recovers.
So it's a really direct point-by-point translation between the two systems.
It really is. It makes the whole correspondence very explicit
Yeah.
and highlights the power of these abstract mathematical structures showing up in such different places.
Okay, stepping back then. What does this all mean? If black holes, these, cosmic monsters, behave like our most advanced AI models when processing information, what are the big takeaways?
Well, first, it strongly suggests that a black hole isn't just a point of no return. It functions as a complex quantum information processing system.
It processes information.
In its own way, yes.
Yeah.
Its radiation, how information emerges, shows these deep parallels with statistical learning. It's not just destroying stuff. It's actively processing it according to rules that look remarkably like learning rules.
That's a pretty fundamental shift in how we think about black holes.
It is. And it's more than just a neat idea. This correspondence potentially opens up really exciting new practical avenues,
Like what?
like using tools developed for understanding AI, things like spectral analysis of data matrices, resolvent methods, measures of model capacity. Maybe we can use those tools to probe fundamental questions in quantum gravity.
Using AI diagnostics to understand black holes? Wow.
It's a fascinating possibility. Imagine analyzing Hawking radiation using techniques designed for large language models.
And could it work the other way? Could black holes teach us about AI?
Absolutely. The paper suggests that too. Maybe principles from black hole thermodynamics, which deal with entropy and information on a cosmic scale, could give us new insights into why AI models generalize, especially in that weird overparameterized regime.
Yeah.
Perhaps understanding the universe's ultimate information scrambler can help us build AI that learns more efficiently or robustly.
So we've taken a deep dive today into a really Astonishing and unexpected connection. We've explored how these seemingly totally separate worlds, black hole physics and quantum machine learning, seem to share fundamental principles about how information is handled, processed, and recovered in really complex, high-dimensional systems.
It's almost like there's a universal information playbook that both cosmology and AI are tapping into.
Yeah, and this kind of cross-disciplinary thinking, it's not just cool, right? It really could unlock entirely new research directions.
Definitely, both in quantum gravity understanding space-time information at its most fundamental and in the future of AI itself.
So here's the final thought to leave you with. If the universe's most extreme information processors, black holes, seem to operate on principles so similar to how our most advanced AI models learn, what does that tell us about the fundamental nature of information itself? Maybe even about the fabric of reality. What other strange connections might be hiding out there, waiting for us to spot these unexpected parallels?